In this video, we're going to look at some Lewis structures, specifically some covalent compounds. When we're doing this, I use a very specific, formulaic, here's what I do, step-by-step approach, and I suggest that you also get into a habit of doing it very structurally. It will help you reduce the number of choices that you have to make. The more complicated a molecule, of course, the more thinking you'll have to do, and the more you'll have to be considering what choices should be made and which ones are the most appropriate. But for this video, we're going to do some very simple compounds. They're not going to have what's called resonance, which you're going to learn about later. They're just straightforward, kind of follow the general rules for drawing Lewis structures for covalent compounds. Alright, so the first one that let's work on today is sulfur dichloride. One thing as you're doing these Lewis structures, I do recommend reminding yourself of naming because these are organic. Alright, because these are in fact covalent compounds, you're going to name them with the prefixes within the name. So sulfur dichloride. The first step you want to do whenever you're making a Lewis compound is you want to decide which of these is the least electronegative. And whichever compound is less electronegative, that goes in the center of the complex. With the exception of hydrogen. If hydrogen is the least electronegative, don't put it in the middle. Put it around the outside and pick another element to go in the middle. So looking at these two compounds, you look and you see chlorine is situated closer to the top right-hand corner of the periodic table. Therefore, chlorine is going to go around the outside, and sulfur, which is the least electronegative, is going to go in the middle. So we know we've got sulfur in the middle, and chlorine is going to go around the outside. This is called a skeleton structure, where you just make a decision about how the different atoms are connected. We haven't made decisions about electrons yet, just the fact that these are connected in space somehow. Next, you want to decide how many electrons do you have. Now we decide that by looking at both our sulfur and our chlorine and looking at our periodic table. So if you go and you look and you find sulfur on the periodic table, where is it located? So you go and you look at your periodic table and you see sulfur is located right underneath oxygen, and it has 6 valence electrons. Our valence electrons are electrons involved in our bonding. So those are the only ones that are important. We're not worried about total electrons at all right now, just valence electrons. So how many valence electrons does sulfur have? 6. Now go find chlorine. It's in group 7, which means it has 7 valence electrons. But you've got 2 chlorines, so I'm going to say times 2. And then I'm going to add this all up because I want to know how many total valence electrons do I have available to place around my Lewis structure. 7 times 2 is 14, plus 6 gives me 20 valence electrons. So I need to put those around my structure. So what I do is I just simply start putting little dots around where every dot is equal to an electron, and remember, every bond is equal to 2 electrons. So I've already drawn 4 on here. I need to start out with my most electronegative. Okay, so as I'm adding little dots around the structure, start out with my most electronegative. So in this case, it's chlorine. And just start adding dots. How many dots should I add? Well, the octet rule is 8. Okay, most elements, not all, as we're going to look at exceptions, not all want to have 8 electrons around the atom. And so chlorine wants to have 8, sulfur wants to have 8. They all want to have 8. So right now, around chlorine, I have drawn 1, 2, 3, 4, 5, 6, 7, 8. I've drawn 8 around chlorine. Chlorine is happy. Let's make the other chlorine happy as well. Alright, both chlorines are happy. I've drawn 8 around this chlorine, 8 around this chlorine to make a total of 16. So I have 4 left. So I can go 1, 2, 3, 4. Is sulfur happy now? Let's see. 1, 2, 3, 4, 5, 6, 7, 8. Yes, absolutely. Sulfur is now happy. Now remember, anytime they share, so anytime you've got a bond, those electrons are shared. So that means in order to decide if the octet of chlorine is full, I'm counting those shared electrons. In order to decide if sulfur has a complete happy octet, I'm counting all of those electrons. And so sulfur is happy, chlorine is happy, and my other chlorine is happy. Each of these are considered to have 8 valence electrons. So I have now drawn my Lewis structure. You don't have to draw these circles around it, okay? Those are just showing you things. Okay, but I've drawn my Lewis structure now. But before I move on and say, I'm done, go back and double check and make sure you have only put the number of electrons on your structure as you have available. The number I have available is when I'm counting however many I counted up here, because that's the number that was on each element. I should not have more and I should not have less than I have put on my structure. So 20. Is that how many I have? I have 8 around here, 8 around here, 16, 17, 18, 19, 20, 20. I'm done. The mistake I see students making is they go 8, 8, 8, 24, I have too many. No, don't count these twice for valence electrons. Just count them for the individual satisfaction of the octet, but don't count them twice whenever you're trying to decide if that matches your total number you have on the compound. All right, so this is my final structure. I could redraw it to make it look a little better without the little circles around it, and it would look the exact same. That's my good, happy Lewis structure for this compound. Let's do another one. Let's do carbon dioxide. So carbon dioxide has a carbon, which is in group 4, so it has 4 valence electrons, and oxygen, group 6, and there are 2 of them. Which means if I add up all of my valence electrons, I should have 12, 13, 14, 15, 16 electrons on my Lewis structure. So now that I've determined the number of valence electrons on carbon dioxide, I can draw the skeleton. It doesn't matter which one you do first, but you're going to have to do them both. So my skeleton could either be carbon in the middle or oxygen, but you want to put the least electronegative in the middle. So it is not oxygen, it is carbon. So carbon goes in the middle, oxygen goes on both sides of it. So now we've got this structure. And then the rules say you start taking those electrons and you place them around the structure until you run out of electrons. I now have drawn 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oxygen's happy because it has 8 around itself, but poor carbon. Carbon is not happy. And we cannot have carbon not happy, because carbon makes up organic life forms, and that's us, all right? So carbon is always happy. It has 4 bonds. It's a pretty stable thing, okay? Not happy. It only has 2. We need to give it more bonds. Okay, well, I just told you we're going to end up with 4, so you probably assume double, and we're good. But let's work backwards. So if we remove this electron pair right here, and I replace it with a bond, that works. Because I did not change the total number of electrons that are on my compound. No, instead I've got 1, 2, 3, 4, 5, 6, 7, 8 on this side and 8 on this side. And so oxygen's happy, the other oxygen's happy, but carbon's still not happy. So I can do the same thing. I remove a pair of electrons and I replace it with a bond. And so now I can count my electrons and decide, do I have 16 electrons on my structure? And then also, is carbon happy and oxygen's happy? Let's check and see. So this oxygen has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. Let's keep counting and get to 16. 9, 10, 11, 12, 13, 14, 15, and 16. And so I have 16 electrons around my carbon dioxide. I'm good. I know my oxygen's happy. This oxygen's happy. What about this carbon? Yep, it's got 8 electrons around it. So each atom is happy, and the whole molecule is happy because I have the correct number of valence electrons distributed about my Lewis structure. And so that's just another example of how you do Lewis structures for covalent compounds. Let's do another example. We've done carbon dioxide now, so let's do carbon monoxide. So carbon monoxide looks like this. Carbon, we know, has 4. Oxygen has 6. To give us a total number of valence electrons of 10 valence electrons. I'm going to put a little line here just so we don't get our species confused with each other. All right, so we've got to redraw now the Lewis structure for carbon monoxide using this information. So you can't really say which one's in the middle because there's 2, so they're connected. There's no middle, okay? But now I'm going to put my electrons around it. So in doing so, start with your most electronegative, and then proceed to your other one. So I've got 10 to draw, and we only have 2 left. That tells me carbon's not happy, I need some more, okay? So erase electron pairs, replace with a bond. Carbon's still not happy because it has 1, 2, 3, 4, 5, 6. So we need to erase and put a bond. Okay. Are we happy now? Let's see. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we have 10 valence electrons available, and we have placed 10 valence electrons on our Lewis structure. Now you said, but I thought you said carbon always has 4 bonds. Yeah, so that's why your carbon monoxide can react pretty easily. You can have another atom come in here and react with your carbon. Okay, so but this is carbon monoxide's Lewis structure. Let's do another one. The next molecule we want to do is carbon hexachloride, what you see here. So with carbon hexachloride, let's decide how many electrons we have available based on our valencies. So sulfur is underneath oxygen again, so we have 6. Chlorine is in the group 7, but there are 6 of them. So 7 times 6 is 42, for a total of 48 valence electrons. Woo, that's going to take me a while to draw. Okay, so let's start drawing it. Let's see what we've got. We know sulfur is going to be the middle. It's the least electronegative. And then there are 6 chlorines around it. So I've now drawn 6 chlorines. But I want you to stop here for a second. Remember our octet rule? Our octet rule said that any of my elements want to have 8 electrons around its outer shell. Whether they're involved in bonding or free electrons, doesn't matter, one's 8. Sulfur, how many does it have right now? 2, 4, 6, 8, 10, 12. It definitely has violated this rule. You know what? It's okay. We'll allow it. Okay? The rule is if you've got something that is like phosphorus or bigger, they can do what's called expanding the octet. Because they have a 3p subshell, they can expand into the 3d subshell. Meaning, once they fill all their electrons from bonds, whenever they've completely filled now the 3p, it can just keep on going and adding more bonds because the 3p and the 3d, the energy levels are available to it. Okay? Don't worry too much more about it right now, but just know that if you are phosphorus or bigger, which sulfur is element 16 and phosphorus is element 15, so it's definitely bigger than phosphorus, so it can have what's called an expanded octet. So if you ever see this happen, or you need to stick extra electrons on the central element, that's fine, as long as they are bigger than phosphorus or phosphorus. Okay? So now let's keep going. Remember, we've got 48 electrons, valence electrons available, and I can now put electrons around my outer elements first, because they're more electronegative, and then my central, if I need to. Okay? So I'm going to do that now. Okay, I have now placed 6 electrons, or 3 more electron pairs around every single chlorine, which means every chlorine or every attachment has 8 electrons in it, because we've got 1, 2, 3, 4, 5, 6, 7, and 8. So that means every group here has 8 valence electrons. So if there's 6 of them, that is 48 electrons, and my valence electrons are satisfied. But what about all my elements? Are my elements satisfied? Definitely. Chlorine has 8 around it. Sulfur, it has 12. So it's got plenty around it. Okay? So this is just another example of how to draw a Lewis structure. In our next video, we are going to look at 2 more covalent compounds. So before you move on and do that next video, I want you to go ahead and try and do both of them on your own. They are both exceptions to the octet rule. And so we're going to try and do boron trichloride and tellurium tetrachloride. So give both of these a try and then start the next video.